Understanding Windows Internals, a foundation for malware analysis. Hey there, mates! Too long didn't read version. To conduct effective malware analysis, it's crucial to understand the internal workings of the Windows operating system. In previous videos, I have already talked about dynamic link libraries. Now I want to cover the user mode, kernel mode, API call flows, and portable executables, including their sections and processes. Therefore, I created this video trying to explain some of these concepts in layman's terms to make it easier to understand. Let's get started, shall we? Windows operates in two main modes, user mode and kernel mode. Let's briefly explore each mode and their significance in malware analysis. User mode. Definition. User mode is where most applications and user processes run. In this mode, applications have limited access to system resources and must interact with the operating system through application programming interfaces, APIs. Characteristics. Limited access to hardware and critical system functions. Processes are isolated from each other, preventing direct access to system resources. Despite the limitations, malware in user mode can manipulate files, registry settings, network connections, and other accessible resources. It may also attempt to escalate privileges to gain more control over the system. Kernel mode. Definition. Kernel mode is a highly privileged mode where the Windows kernel runs. It has unrestricted access to system resources, hardware, and critical functions. Characteristics. Provides core operating system services, manages system resources, and ensures security and stability. Device drivers, which facilitate communication with hardware devices, also run in kernel mode. Malware operating in kernel mode can exert extensive control over the system, manipulate system behavior, conceal its presence, intercept system calls, and tamper with security mechanisms. Understanding the distinction between user mode and kernel mode is fundamental for analyzing malware. Malware can operate differently depending on the mode it infiltrates. In user mode, malware might be limited in its impact but still capable of significant damage, while in kernel mode, it can achieve more profound and potentially devastating control over the system. Now, let's analyze the following diagram to guide us through the different components and how they interact. Let's get started. The Windows operating system is designed with both user mode and kernel mode components, each playing a distinct role in the system's functionality. The diagram we're looking at simplifies this architecture to help us grasp the essential parts. Key components. 1. System support. Processes. These are fundamental processes that manage critical system functions, like the logon process and the session manager. Think of them as the behind-the-scenes operators that keep the system running smoothly. 2. Service processes. These processes handle various services that run in the background. For example, the task scheduler, which manages the scheduling of tasks like web backups and updates. 3. User applications. This is where your typical applications, such as your web browser or text editor, run. They can be either 32-bit or 64-bit applications. 4. Environment subsystems. These subsystems support different operating environments. For instance, they enable compatibility with older applications designed for earlier versions of Windows. User mode and kernel mode. The architecture is divided into two main layers. User mode, subsystem, DLLs. These dynamic link libraries provide various functions that applications need, like user interfaces and file operations. They act as intermediaries between applications and the core system services. ntdll. This is a special DLL that bridges user mode and kernel mode. It handles low-level tasks and communicates directly with the Windows kernel. Kernel mode, kernel, the heart of the operating system. managing core functions such as memory management, process scheduling, and system security. Device drivers. These drivers allow the operating system to communicate with hardware devices like your keyboard, mouse, and printer. Hardware abstraction. Layer HAL. HAL abstracts the hardware details, providing a uniform platform for the kernel and device drivers to interact with the hardware. Detailed view. At the bottom of the diagram, we see the executive components. Kernel manages fundamental OS operations and ensures everything runs smoothly. Device drivers facilitate communication between the OS and hardware devices. HAL hardware abstraction layer hides hardware specifics from the rest of the OS, making it easier to support different hardware platforms. Windows API call flow. Explained. Simplifying the complexity. We're going to simplify the concept of Windows API call flow and break down the diagram to help you understand how applications interact with the operating system. This is a key concept in malware analysis and understanding how software operates on a deeper level. Let's dive in. What is Windows API call flow? When an application wants to perform certain operations, such as reading memory or accessing hardware, it needs to communicate with the Windows operating system. This communication happens through the Windows API, Application Programming Interface. The API call flow is the process by which an application requests services from the operating system. Breaking down the diagram. Let's walk through the diagram step by step. 1. User application, shell.exe. This is the starting point. A user application, like a shell program, wants to perform a specific operation. In this case, reading the memory of another process. 2. Kernel 32. DL. The application first interacts with kernel 32. DL, a core part of the Windows API that provides functions for memory management, input-output operations, and more. It calls the read process memory function here. 3. ntdll.dll. The request then passes to ntdll.dll, which acts as a bridge between the high-level API calls and the low-level system calls. The function here, ntred virtual memory, translates the request into a format that the operating system kernel can understand. 4. System call, syscall table. This is where the transition from user mode to kernel mode happens. The request moves to the syscall table, which contains pointers to kernel functions. The system call mechanism allows user applications to request kernel services safely. 5. Kernel mode, execution. In kernel mode, the actual operation is performed by the ntread virtual memory function. This function accesses the memory as requested by the application. 6. Returning the result. Once the operation is complete, the result is passed back through the same layers in reverse order, from kernel mode to user mode, through ntdll.dll and kernel 32, DL, and finally back to the user application. Imagine you want to send a letter to a government office, kernel. You write your letter, user application, and drop it at the local post office, kernel 32, DL. The local post office then forwards it to the central processing facility, ntdll.dll, which sorts and prepares the letter for final delivery. The central facility uses a special channel, a syscall table, to deliver the letter directly to the government office, kernel function. Once the office processes your request, the response is sent back through the same channels, eventually reaching you. Why is this important? Understanding the windows. API call flow is crucial for malware analysis because many types of malware exploit these processes to perform unauthorized actions. By knowing how these calls work, analysts can identify suspicious activities and defend against potential threats. What is a portable executable, PE? A portable executable, PE, is a file format used by Windows to encapsulate executable programs. DLLs, dynamic link libraries, and other system components. Think of it as a box containing everything a program needs to run, including code, data, and resources. PE file structure. The PE file format is organized into several sections, each serving a specific purpose. Here's a simple breakdown. 1. Text section, status text. Description. This section holds the executable code of the program. Importance. It's the core of the program's instructions and often a focus in malware analysis for detecting harmful code. 2. Data section, .data. Description. Stores initialize global and static data variables. Importance. Contains vital data that the program uses during execution. 3. Read-only initialized data, our data. Description. Contains read-only data like constants, string literals, and initialized variables. Importance. Essential for storing constant data that shouldn't change while the program runs. 4. Exception information, .pdata. Description includes function. Table entries for exception handling. Importance. Manages errors and exceptions that occur during program execution. 5. BSS section, recent is. Description. Holds uninitialized global and static data variables. Importance. This data is set to 0 when the program starts, even though it's not initialized in the file itself. 6. Resource section, Description. Stores resources like images, icons, strings, and version information. Importance. Critical for the graphical elements and metadata of the program. 7. Import section, data. Description. Lists. Functions imported from other DLLs. Importance. Shows dependencies on external libraries, crucial for understanding the program's interactions with other software. 8. Export section, data. Description. Details functions exported by the executable. Importance. Allows other programs to use the functions provided by this executable. 9. Relocation section, .reloc. Description. Contains information for relocating the executable's code and data when loaded at a different memory address. Importance. Ensures the program runs correctly no matter where it is loaded in memory. Visualizing PE sections. To better understand the structure of a PE file, you can use tools like PestStudio. These tools help visualize and analyze the sections, offering insights into the file's composition and highlighting any potential malicious content. Understanding processes. A process in computing is an instance of an executing program. It represents a running application and consists of various resources such as memory, file handles, and security contexts. Here's a simplified breakdown. 1. Private address. Space. Description. The memory space allocated for the process's execution. Importance. Isolates the process's memory from other processes, enhancing security and stability. 2. Private handle. Table. Description. A table that keeps track of the handles or references to system resources like files and devices. Importance. Manages the process's access to these resources efficiently. 3. Threads. Description. The smallest unit of execution within the process. Importance. Enables the process to perform multiple tasks simultaneously, improving performance. 4. Access token. Description. Contains information about the security context of the process, including user permissions. Importance. Ensures the process operates within the rights and permissions granted to the user. By the way, if you enjoyed this content and would like to support us, our donation links are in the description of this video down below. I'll see you guys in the next one. Stay safe and alert out there.